Okay, so what's the verdict here?
Well, we found the area and the size.
Okay, team, right, team inscribe. What was your strategy here? What'd you do?
We made like 4 rectangles.
Okay, 4 rectangles. I'm assuming, how wide is each rectangle?
Half an inch.
Half of a whatever, okay.
Half of an inch.
Gotcha, okay. So they look like that?
Yeah.
It's red, line.
And then how tall is that one?
It's not.
Not tall at all, okay, it's got no height, good. And so the height, how tall is, okay, so what'd you get for the area of this one?
4.5.
4.5 for the area of this one.
Oh, no. For just that initial one, 1.875.
Slow
Okay.
your roll, chief.
1.875.
Oh, 875, whoops, all right. Let's get this straight here. There we go. Okay.
Oh god, yeah, somewhere in there. Okay, next one,
Mm-hmm.
1.5.
Okay.
And then 0.875.
Okay, good. And you're getting those by multiplying 1/2 by
The height.
the height, and the height right here would just be
0.5 and then f of
4 minus 0.5 squared?
Yeah.
Okay, everybody see that? Okay, good. And that came up with a total area of
4.25.
4.25 is our green area. Okay, good. Okay, team circumscribe?
How about it? Same thing with rectangles touching on the left side.
Okay, green team, inscribe team.
Rectangles touch on the left side.
Ah, okay.
Right side.
Okay, now let's look at at the rectangles that touch on the left side now. So the first one's gonna be, I'll just draw the extra, right, so they're behind. Now what do you notice about the second one?
It's more bigger.
It's more bigger, okay? It's more bigger, good.
Good choice of word.
I might even look for something more profound than more bigger here in a second. So
Extremely bigger.
it looks like that, right? Okay, adding up those areas. Let me rephrase this. Why do I really only need to write down one number for your sum and the rest is work I've already done?
Because the last one's the same as the
Yes. Okay, good. You see the trick? You see how that's related. Notice that the height of the circumscribed rectangles are the very same as the heights of the inscribed rectangles to their left in this case, because the function's going down, right? Okay, that's always going to be the case. They're always just going to differ. Only the end ones are the ones that potentially can differ, right? Does that make sense? So really all we have to do is just add up these two go together, these two go together, and these two go together, and the only one we have to really add up in addition is that first one, and that's a pretty easy one. What's the area of that one? 2, isn't it? Yeah, because the height is 4, and the width is 0.5, so that area is 2, and so I bet you came up with 6.25 for your answer, right? Make sense? Okay, good. Now, this is honestly the way, I would say that whenever, I don't know what the exact rule is, you can decide for yourself. For me, it's about n equals 8, where n is the number of rectangles. If you have less than about 8, it's honestly probably better just to add them up that way, really. Now, when you start to get up to numbers bigger than 8, like if you had 20, for example, you don't want to be adding those up individually. Then we want to come up with some kind of a more organized, systematic way of doing it, where we can maybe come up with a formula that we can add up more efficiently, okay? And so that's what we're going to do today. We want to push this thing out a little bit so we can deal with sort of intermediate estimates. And then eventually, later this week, we'll be in here at least one more day this week. We'll look at how can we make an exact estimate. How can we get one that is perfect, that's exactly correct. Okay, and there's a really cool trick that we can do there, which you guys, I'm sure, will all come up with. Okay, so how do we do something then like this? How do we extend this to where, let's just take a general function again. So how about if we've got f of x, and we want to add up the area under this function from A up to B, but we want to add it up for a big number of rectangles. In fact, let's say we just want to add it up for n rectangles. We're not even going to specify how many they are. We should be able to choose based on n. That should just have an impact on our formula. Okay? Well, let's look at this in the same manner that we've been looking at these rectangles, right? We've been slicing these things vertically, slicing them uniformly, right? And so if we're going to slice this thing, so we've got n rectangles, and the width goes from A to B, what is the individual width of each rectangle going to be? And we'll call that delta x, by the way. So delta x, delta just, that makes sense, doesn't it? Delta just means change in x. So that's going to be, we've got this distance on the x-axis that that our area is covering, and we're going to slice that up into pieces, and each piece would be a delta x width. What's my formula going to be for delta x then? B minus A over n, sure. It's the total width divided by the number of rectangles. Tells us how wide each individual rectangle is, correct? Okay? So we're going to slice this thing up into these pieces, each with a width delta x, etc., etc., like so. Okay, and if we're looking at, in this case, let's go ahead and look at the circumscribed rectangles. Okay, so we'll look at these ones right here. Okay, how are we going to pick one of these in general? Let's just pick this one in the middle, and this is going to sound a little strange, but we're going to pick the ith. So this is the first, second, third. What's this one going to be? Say it again. I think I heard it. Maybe I didn't. Wishful thinking. What is it again? The nth, yeah. Right, that's going to be the nth rectangle. What's this one going to be?
Minus 1.
N minus 1, yeah. Let's call this one the ith. What in the world is I mean?
Imaginary.
No, not imaginary. Thankfully, it's not imaginary.
Thank gosh.
Say it again. Well, kind of. It's I stands literally for index, and you'll remember talking about. Now, this is going to take you back. What is this sort of reminding you of when you start adding up numbers of things?
Oh, is it the average of the bottom and then the average of the average height of?
Well, I mean, not exactly. I see what you're getting at, but not exactly. I want you to think here, almost just lose sight of the picture for a second, but just remember what we're doing. We're adding up a bunch of discrete areas, aren't we? Right? We don't even know how many there are. We're going to leave that up in the air, n, right? But when we add those up, we have to add them up one at a time, right? And so to keep track of which piece we're adding up, we're going to call that I. Doesn't that seem an awful lot? Does that remind you of something you did last year? Summations, yeah, exactly. It reminds you of summations, right, of discrete sums. Okay, so it reminds you probably of stuff like this, where you did a sum of terms, right,
Oh.
as the number of terms. You're going to add them up one at a time, and you're going to start with the first one, and you're going to end with the last one. And I is just the index variable, which just keeps track of which one am I on, which one am I adding up, right? Okay, this is going to seem a little disjointed, but we're going to move in this direction anyway. So let's just quickly, I want you to start thinking about these just a little bit. We'll talk more about it in a second, but I want you to maybe tell me, what is this sum? You don't have to give me a number answer, but what does that sum look like?
10.
Give 1. 1 plus, right, because we're adding these up, 1
Oh, you got
plus 2 plus
3,
3,
4,
and that's it, isn't it? Right?
10.
Okay, so the answer would be 10, yeah, okay, all right?
Woo, yeah!
Yeah, I was just saying, can't skip a couple lines in the script.
Yeah.
It's improvisation, right? You gotta go with it.
I know.
Gotta make sure I don't seem like I'm reading from the script. Can't be like that.
Okay, what's that one gonna look like? How'd you get 5? Oh, okay, so we get 2 times 2 plus 1 plus, see how we're doing this?
Yeah.
Yeah, that's a lot.
Right, et cetera, right?
So I just goes up to read that.
Exactly, so I has to move up in discrete increments, and this is its starting value, and we're just gonna add up all the terms where I migrates from that number up to that number. And that's really all it is, okay? Now, we'll leave this stuff, we're gonna come back to this, but does it just make sense here conceptually that, boy, that seems to fit pretty well, that idea fits pretty well what we're trying to accomplish here, doesn't it, right? Because really what we're trying to do is we're trying to add up a bunch of discrete areas in this case. But, you know, this expression right here, it doesn't really, it doesn't really mean anything, but it could, right? It could represent an area of a rectangle, okay? All right, so we'll come back to that. Okay, back to our picture. Okay, so now how are we going to do this? If we could just come up with the area of the ith rectangle, then we could add all those up, couldn't we? Right? So somehow we got to name this guy. We got to name the area of that. Now, what is the area going to depend on here? Okay, it's going to depend on delta x, because that's the width, and it's going to depend on the height, right? Okay. Now, but the height is determined how? Okay, by the function, right? The height is determined by the value of the function, and the value of the function is determined by, you know, how far along, you know, the x value, isn't it? Right?
Yeah.
So really what this all boils down to, if we could just come up with, in this case, the height is determined by the right-hand edge, isn't it? Okay? So if we could come up with this value of x right there for that ith rectangle, we'd have everything we need, wouldn't we? Right? To come up with an area function. Everybody agree? Because if I knew that x value, I could plug it into the function to get the height, right? And then the width is just that. Agree? And that's all stuff we'd have to be given. This wouldn't make any sense to do unless we knew we're adding up an area from here to here, right? And we're going to slice it into this many rectangles. And then that gives us automatically the width of each individual rectangle, right? So how are we going to do that? How could you tell me what is that value right there based on I? What is that x value? So we need to know, in other words, we need to know this distance, right? That's, actually what we really need to know is that distance, isn't it? Okay, and what we might call that, if we had to give that a name, we might call that x sub I. Okay. Suggestions? If I had to name that distance, it's really two parts, isn't it? I've got where I start to begin with, plus how far I've progressed through the area. Okay, think of so think of it this way then. Think of it in a sense as just starting on A, right? And then I'm gonna take, to traverse this area, I'm just gonna take a total of n steps, right? So you cut it into n pieces. Each step just corresponds to the width of a rectangle. Well, how many steps have I taken to get there, to the right edge of this thing? I, haven't I? Because there's 1 step, 2 steps, 3 steps, etc., 4, 5, 6. At the end of the ith step, I am at, right, does that make sense? I'm at the right edge of that rectangle, which in this case is determining the height. So how would I say that then? If I've taken I steps, how much distance have I covered? I times delta x, right? Because the width of each step is just the width of the rectangle. So it's just I delta x, isn't it? Okay, so then, so this distance right here is really just my starting point, right? Plus I delta x. Make sense? Okay, and that's all we needed, right? Because now if we want to get the area of this rectangle, the area of the ith rectangle, call it A sub I, how about, is equal to the height of the function, which is going to be this amount right here. Well, isn't that just going to be, I've got x, whoops, sorry, I've got the x value we called x sub I. What's the y value going to be? F of x sub I. Right, so that's the height. And the width is delta x, right? So it just looks like, and x sub I is just that, isn't it? A plus I delta x. So this just looks like f of A plus I delta x times delta x. Where delta x is always just b minus a over n. Okay? So let's see if we can use that formula now to add up. Let's add up what the inscribed area would be under, let's go back to this guy. Let's go back to this one. And we're going to add up the, actually let's not do that one. Let's do a different one. Let's do this guy. See if you can come up with an area formula for adding up the area under the curve x squared plus 1 from 1 to 3. So that's the area we're trying to find. And let's find it with, set up a formula for finding it with 24 rectangles.
Okay.
So what we really just need to know then is that ith rectangle is going to be the area of that. Take a second, experience, and then we'll see if we can come up with the answer as a group. Okay, so did we come up with an answer here? What are we going to get? So what's A in this case? 1. A is 1, right? Because that's AB. N is 24, right?
Yeah.
Okay, there's our function. And didn't we just say earlier that the area, that if we're looking at the area of this guy right here, we'll call it A sub I. A sub I was what? It's just height times width. What was the height?
1, 3.
Minus delta x or something like that.
Okay, yes, the value of the function there, right? At x sub I. Okay, and what was that? So we start at 1 plus I steps of width delta x, right? So f of starting x value plus we've taken I of those steps over, right?
Wait, why is
Makes
it
sense?
one? Cause it starts at one?
Because it starts at one,
Okay.
right? We're starting, does that make sense?
Yeah.
Okay. We started here and we took I steps over to there.
And then
Now-
delta X is the change in,
It's the width of one of these things.
oh,
Right?
Yeah.
Okay.
Yes, much more.
So there's the area, right? There's the ith area. Notice that it's in terms of I, right?
okay.
So now how could we add that up as a sum? If I want to add up the total area, that's just going to be the sum of the ith area as the ith rectangle transitions from the first to the, how many we have?
24.
24, right? So it's going to be this. So that's our formula. We just need to plug in the specifics, right? In fact, it's always going to look every time. Well, at least every time that we're adding up the areas based on the right-hand edge of the intervals, right? Because that's what we've done, isn't it? We've started at one and we've taken I steps to get to the right edge. Okay. So in the case of a rising function, increasing function, we're creating circumscribed rectangles. Now, what if the function were decreasing? Then the right-hand edge would be giving us inscribed rectangles, right? Okay, but remember that there's two ways we can weed out the imperfections in our strategy. We can either average the two, which is kind of a pain, but you also told me we could just increase the number of rectangles, right? And so eventually it's not going to matter whether they're inscribed or circumscribed. If we can add up enough of them, we get a really good approximation either way, right? Okay, so hold on to that thought. We'll come back to that later too. Okay, so then it's always just going to look like f of a plus I delta x if we're doing the right-hand edge times delta x every time, right? We just need to plug in the specifics for our case here. We have our own unique function. We've defined our own values of a and b, and we've defined a certain number of rectangles. When we plug in those specifics, we get the discrete sum for our particular problem, right? So what do we get? So our area equals the sum from 1 to 24 of f of, what's our a again? 1 plus I times, now what's our delta x going to be?
112.
What's it going to be?
112.
112. So we get, 3 minus 1 over 24. So 112. Each one has a width of 112. Okay, makes sense. So that's the same thing as saying I over 12, right? Times the width, which is 112, right? Okay, now f of x for us is x squared plus 1. So what's f of 2?
5?
5, right? 2 squared plus 1. What's f of q? Okay, what's f of hand? Okay, so what's f of 1 plus I over 12? The quantity 1 plus I over 12 squared plus 1, right? Is that what it was, plus 1? Yeah, okay. So this stuff right here then just becomes 1 plus I over 12 squared plus 1, right? So we're adding up the sum of that times 112. And that's all we have to do, okay? So what's the potential dilemma with this? As you're looking at this from a practical perspective, you're gonna have to do some of these. What are you probably saying? Uh-oh, okay, I get it, but it doesn't look like a lot of fun because why? Because what?
It's a lot of work.
It's a lot of work, okay? That's a lot of numbers to add up. What if our sum went to 240?
You'd be screwed.
Well, you don't want to add those up by hand, do you? So we need, but there are methods for doing this. Now, the road can split here. one method we could take is graphing calculators. Let the graphing calculators add up those discrete sums for us. I'm gonna show you how to do that. The other route we could take is we could rely on some known discrete sums. Okay, there are some discrete sums that we use an awful lot. And they show up in your book, but here's a short list of ones that it's good to know. The sum of 1, or I'll just make it a constant. And you can tell me what this is gonna be. This is one you can absolutely tell me. From 1 to n, the sum of c, where c is some constant, is what? So it's gonna be c plus c plus c n times. So what's that? How would you say that?
C to the n.
Not c to the n.
C times it?
C times n, wouldn't it? Right? Because if you have, what if n were 5? You'd have c plus, you'd have 5 c's added up. That's just 5 times c, right?
Oh,
So this one's just gonna be cn. So there's one we need to know. How about the sum of I from 1 to n? Now that's a little tougher one. And if we had more time, I'd let you guys, we'd use some inductive reasoning and come up with this one on our own. But I don't want to take the time to do that. Okay, this one, I gotta remember here, this one is n times n plus 1 over 2. I really ought to probably check myself on that. I'm pretty sure that's right. Okay, and the sum of I squared from 1 to n is, oh man, I'm gonna forget these. It's, I better look these up. I think it's 2n plus 1 times n plus 1. I'm pretty sure that's it, but
we've got 5 minutes.
okay, yeah, well, that's all we need. We're about done. I don't want to get this wrong. I think it's n times n plus 1 times 2n plus 1 over 6. But I haven't looked at this in a year, so I better double check myself. That's right. Oh, okay, good. Not losing it yet. Close. And then the sum of I cubed from 1 to n is just n squared times n plus 1 squared over 4. Okay, so the nice thing about those, and that's all we're going to do. Those are handy ones because those are power functions of I, and so those are the terms that would appear if we had like a polynomial or something even like this, right? Where we've got a binomial that we're going to expand. When I expand that, I'm just going to get some constants plus the powers of I up to I squared. Agreed? Okay, and so I could add up those contributions term by term in a discrete sum, just using those for summation formulas. Okay, that sounds like a lot of mumbo jumbo, so let's just look at what would that look like for this particular problem. So let's grab this guy and go to the next page. See if we can wrap up this one for today. And you'll see this isn't that big a deal. It's pretty cool that we can do this. And then tomorrow I'll show you how to do this on a graphing calculator. Okay, so what does this look like now? Let's do the algebra first of all. And I'm not going to do a complete review of sigma notation stuff, but as we go through it, I think I'll answer questions, and I bet a lot of this will come back. So we need to expand this out so it looks like a sum of terms, right? So what does 1 plus I over 12 squared look like when I expand it? So this part right here just becomes 1 plus, yeah, it's going to be, a plus b is just a squared plus 2ab plus b squared, right? So 2ab would just, that's a and that's b, that would just be what, I over 6? Plus I over 12 quantity squared, so I squared over 144. Okay, so that's all this stuff. Then I've got to add 1 to that, so that's going to just get grouped with this guy, right? Everybody agree? And so we end up with the sum of 112 times 2 plus I over 6 plus I squared over 144, as I goes from 1 to 24, right? Okay, what can we do with sigma stuff? Now, you would have done hopefully quite a bit of this last year. When we're adding up sums, what would be the best way to do this, you think? Can I break up sums into, here, let's take a look at an example. What if I had an easier one to maybe help you break this apart? What if I had the sum of I plus 1 from 1 to 4, right? Isn't that equal to 1 plus 1 plus 2 plus 1 plus 3 plus 1 plus 4 plus 1?
Yeah.
Right? Isn't that also just equal to, if I get rid of the parentheses, 1 plus 2 plus 3 plus 4 plus 1 plus 1 plus 1 plus 1? I'm like an extra 20 minutes here. Okay. Okay, I will put up an assignment that you can start. It'll start with some of the stuff we did like at the beginning of the period.